This is a video related to solving first order linear differential equations. You'll recall from the notes that a first order linear differential equation is of the form dy dt is equal to a of ty plus b of t. Okay. And if we're trying to put this in the context, of exact differential equations, which we have already covered, we could then view dy dt as equal to the differential equation minus negative a of t y minus b of t divided by 1. So this is saying that dy dt is equal to negative t of t comma y over y of t comma y. So in this case, our function t of ty, as in the exact equation notes, is minus a of ty minus b of t, and y of t comma y is equal to 1. Okay, and this is exactly what the first part of our notes that we had for this section are emphasizing. Okay, so equation 14 is saying exactly what I've written over here to the right. Okay, now continuing on, we can see that as it stands, the differential equation, that the vector field that comes from this differential equation is minus a of t y minus b of t comma 1, and we can see that the partial derivative of t with respect to y does not equal to the partial derivative of y with respect to t. Okay, so this implies that f is not a conservative field as it stands, which is also known as there does not exist a potential function phi. Okay, so but we were able to fix that with an integrating factor. So recall that if we took this first order linear differential equation and defined the term mu, which was e to the integral of negative a of t dt, that if we did that, then we could define a new vector field, okay, dependent on t and y, and it was mu multiplied by the original t and then mu times the original y, which were t and y were given as over here. Okay, so we showed here that that this would become a new function t, and this would become a new function y. Okay, and then this vector field f, boldface f, is conservative, which implies that there does exist a potential function. Okay, and since there did exist a potential function, we could go through the formula for it just as we did for exact equations. It would be the integral of boldface t, integrate with respect to t, plus the integral of percent symbol, where percent symbol is given by boldfaced y minus the integral, the partial derivative of y with respect to boldface t with respect to y, and then integrate all that with respect to t. Okay, so this was our solution method. We first needed to find the new vector field, find new vector field, and then 2, find the potential function from it. Okay, so why don't we go through a specific example here to show how all of this works. Okay, so let me just pick an example from our course notes. I will just go ahead and pick, say, number, why don't I pick number 10 since it's an even number. So why don't we go ahead and try to solve the specific equation, okay, dy dt plus 3y is equal to cosine of 2t. And we know that the function evaluated at 0 is -1. That's the initial condition. Okay. So here's a problem we will try to work through. Okay. Now we can see here that dy dt, we need to put it into the correct form. This is -3y plus cosine of 2t. Okay. Which implies that our function a of t is equal to -3 and our function b of t is cosine of 2t. Okay. And therefore we know our original vector field is minus a of t y plus b of t comma 1. So that would lead to 3y minus cosine of 2t comma 1. That's our original vector field. But we then needed to find, this was not conservative. There did not exist a potential function, so we need to now find our new vector field by doing mu multiplied by minus a of t y plus b of t, 1. Okay. And our integrating factor mu in this problem, mu is equal to e to the integral minus a of t dt. But a is equal to -3, so minus a is equal to 3. So we integrate e to the 3 dt, which tells us that our integrating factor is e to the 3t. Okay, so our new vector field is equal to e to the 3t multiplied by 3y minus cosine of 2t multiply 1 multiplied by mu here. So it'd be e to the 3t times 1. So here's our new vector field. Okay. Our new vector field f, I simplify a little step further here, f is equal to 3 e to the 3t y minus e to the 3t cosine of 2t e to the 3t. So here's our new function, capital T. Here's our new function, capital Y. Okay. And according to our potential function, we need to just integrate t and y according to the steps that we had in the notes. Okay. So we need to take that function t and y, and we need to use them in this formula number 20 right here. Okay. If you go through that series of steps, okay, you can follow the formula. And I'll let you do that. Okay, let me show you what the answer will come out to be, the answer. Okay, and then we can talk about the steps. Then we can talk about some more features. Okay, so I'm going to go over here and I'm going to do exactly what I said. We've put in the integrating factor. Okay, we've come up with our new differential equation. The first entry of that is capital T. It's 3 times the exponential function, 3 times t, but t is x in this case. That's what this particular program once, times y minus exp 3 times t times cosine of 2 times t. Okay. There's our input, our function capital T, the new function that involves the integrating factor. Let's go ahead and put in our mu times 1 term here, that's e to the 3 times t. And I think we had our differential equation that the initial condition, what was the initial condition for this problem? I think we had decided that y of 0 was equal to 1, right up here. So I'm going to put in my initial condition, y of 0 is equal to 1. So the initial value is 0 and the y value at that initial value is 1. Okay. We can run through this solution method. Okay, let me show you what happens. Let me make this a little bit bigger. So now we can see, oh, sorry, my t's need to be x's. For this code, the function needs to be functions of x, not t, x and y, not t. Okay, I will rerun this code. So here is our solution that we are supposed to get. Okay? You can see here that our potential function when you integrate comes out to be this. Okay? And when they apply the initial condition, you get a constant of 10 over 13. Okay? So let me bring back in, let's do some pencil and paper work now. Okay, with this answer. Let me bring back in our notes over here. Okay, let's see what we can see. Okay, so let me rewrite our solution that we had. Okay, so our solution comes out to be phi of t comma y, okay, is minus 1/13 e to the 3t multiplied by minus 13y plus 3 cosine of 2t plus 2 sine of 2t. I will move the code out of the way in just a second. And then our constant is equal to 10 over 13. Okay. So here's our solution. Okay. Now observe, if you do a little algebra on this problem, okay, my claim is that the algebra that is phi of t comma y equal to a constant can be solved for the function y. Okay, we can actually take this implicit formula here for y and solve it explicitly for y. So if we work through the algebra here, we'll get just distribute the negative 1/13 e to the 3t through. You will get the negative 13's cancel. You get y e to the 3t minus 3 over 13 e to the 3t cosine of 2t minus 2 over 13 e to the 3t sine of 2t, and that's equal to 10 over 13. Okay. Now notice that here is the only y in this problem, so we can make our way towards solving for y. I will move everything to the other side, 3 over 13 e to the 3t cosine of 2t, adding 2 over 13 e to the 3t sine of 2t to the other side, and then we have 10 over 13. Okay. And now we can divide both sides by e to the 3t. and that leaves y all by itself as a function of t. You'll get 3 over 13. The e to the 3t's here cancel, and you're left with cosine of 2t. E to the 3t's cancel, and you're left with 2 over 13 sine of 2t. And then you're left with plus 10 over 13 e to the 3t. So there is your explicit solution for y in terms of the variable t. And this solution, y of t, solves the initial value problem. Okay, so notice that at 0 times 0, you get cosine of 0 is 1, so that would be 3 over 13. This term sine of 0 goes away. 10 over 13 e to the 0 is 1, so you get plus 10 over 13, and you do in fact get 13 over 13 is equal to 1. So this is our solution to our differential equation, and it does in fact go through the initial condition involved. Okay? So my claim here is that for first order linear differential equations, the function you get here for phi can actually be solved for y of t. Okay? And that is represented in our course notes right here as you had a homework problem to work out the details that this potential function phi for a first order linear equation, that you can actually solve it for y as this equation. So this is the general formula here. We can see that here is our constant divided by mu, right? That is the term that's sitting right here. Mu, remember, was e to the 3t. And that must mean that this 13, the cosine and sine terms, are what happen when you compute this integral out. Okay? So that is, I hope, a complete solution to this first order linear differential equation without minus sign errors. I know we had some trouble in class with the minus sign, so this should fix any of those kind of questions I hope that you have. One last thing I would say here, if you want to check, if you'd like to check your solution here to this differential equation, you can go to the demos again, solution finder and plotter. You can put in this differential equation just all by itself. What did we say our differential equation that we were looking at? Let me remind myself here was, yes, minus 3y, minus 3 times y plus cosine of 2t. And we decided that in this problem that the initial condition was y of 0 is equal to 1 or negative 1. Did we do 1 or negative 1? Well, if you put 1, run this problem, okay, it will show you the solution as an explicit solution. So here, if you expand this out, you will get the solution. And I can't remember if we did have initial condition of negative 1, you just change the negative 1, and then you can compare. I can't remember which initial condition we used on the previous problem, but here we go. Either way, you can check your solution against this. And also you can see that the plot, what does our solution look like? Right. And there is our solution. Okay. getting this worked out a little bit here. You can see here the terminology from class that when the time first starts out, there's your initial condition. Let time move on. And our homogeneous solution, or the transient part here, starts to work its way out, and as the more time goes on, our solution approaches your particular solution, which is the steady state solution here. So you can see that this initial kind of weirdness goes away, and it just leaves eventually just this regular solution plot. So this is unique. This is a common feature of first order linear equations. And that would constitute a complete solution to this problem.